So hello and welcome to another video from sickmaths.co.uk, where you can find lots of free GCSE, GCSE A-Level and Key Stage 3 maths videos. This video is about binomial expansions for the CT A-Level maths module under Edexcel, which is basically about expanding brackets. Okay, I'm going to teach you some principles over here. Yes, you could use it for working out small powers. Okay, in fact you can use this method over here for any powers, but it's not advised, and you'll see why when you try it out. Okay, basically, here are some very important principles, beginning with Pascal's triangle. Okay, Pascal's triangle is at the heart of this subject, really. Okay, so this is Pascal's triangle. It's a pyramid of numbers, and you can see the numbers are generated by adding up the numbers above them. So 1 plus 1 makes 2, 1 plus 2 makes 3, 3 plus 3 makes 6, and it can go on and on and on. And each row tells you a different expansion. Okay, so this row tells you a plus b squared, this row tells you a plus b cubed, and you can see that by looking at the second number in each row. So this 4 tells you is for the a plus b to the power 4 expansion. Okay, where by the way a and b can be anything. Basically you can expand anything. So this is sort of your a and that's your b in this particular example. You'll see that in more detail shortly. Okay, so basically how does Pascal's triangle help you with this expansion? Well, a and b follow a certain pattern in this expansion that you don't need Pascal's triangle for. It just goes, a to the power 4, because you've got this power here. It tells you what power to start with in your expansion. So it goes a to the power 4, then a cubed, then a squared, then a, then no a, and b does the reverse, no b's, then b's, and b squared, b cubed, and then b to the power 4. Okay, so this power tells you what power to start with and end with. Okay, and you don't need Pascal's triangle for that. What you do need it for is what number to put in front of each element of this expansion. When I mean by an element, I mean each bit, sort of separated by these pluses. Okay, you could have minuses, I suppose. But anyway, so what the proper name for each of these numbers is the coefficient. Okay, this is the coefficient of a to the power 4. This is the coefficient of a cubed b. Okay, you might have heard those words before. Anyway, so where do these numbers come from? It comes from Pascal's triangle. This 1 gives you this one. This 1 over here gives you this one. This 4 gives you this 4, the second number. Okay, in that order. So that 1 gives you the number in front of the first element of the expansion. That 4 gives you the second element of the expansion. Okay, now what I want you to take away from this part of the video is that Pascal's triangle is symmetrical. That means the coefficients, these numbers in front of each element, okay, are going to follow a symmetrical pattern. So if you start with 1, you're going to end with 1. Well, you're always going to start and end with 1. That's another thing I want you to learn. Okay, now if you're doing a plus b to the power 4, you have to use this row, because the second number in each row tells you what expansion you're doing. So if you got a 4, that means you're doing a plus b to the power 4. The next row is going to have a 5 in it. 1 plus 4 makes 5. That's going to be for the a plus b to the power 5 expansion. Okay, so that's another important thing. The second number is going to be, the second coefficient is just going to be the power of the expansion. Okay, and that's basically it. So it begins with 1, is symmetrical, and the second number is the power. Okay, the second coefficient, and the second to last coefficient is the power. Okay, so that's what you have to take away from here. Now you don't see Pascal's triangle being used here, but these things here, which I want to talk about in a bit, actually are generating the numbers from Pascal's triangle. Okay, so let's just talk about it now. The main method, a plus b to the power n. Okay, where a and b can be anything, like I said earlier on, and n is the power for the expansion. And so how does it work? Well, it follows this pattern, okay, and I suppose another thing you have to take away from here is that this pattern for the a's and b's is applied in every expansion for any power. Okay, so I say it here. I've just written it slightly differently over here, haven't I? A n B naught, yeah, using algebra obviously, but also I mentioned the B over here, which I didn't really mention there, because B to the naught is just one which doesn't need to be mentioned, but I mention it because when you read it yourself slowly, which you really should afterwards, you'll I think you'll find it easier to memorize with the A and B in every single place. And also things like this 0 matching with this 0, this 1 matching with this 1, and other things that when you look at it you go, oh okay, that's really easy to remember, like, the powers always add up to n, n minus 1 plus 1, n minus 2 plus 2, etc, etc, etc. Anyway, so that's that. But taking away another thing we learned from Pascal's triangle is that the first coefficient, this is going to produce the first coefficient, is always 1. The second coefficient is always n. Now you might think, why did I bother writing that? Oh, again, it's just for the pattern, so you can easily see a general pattern, okay? But this one you have to work out, The last one you don't, and the second to last one you don't, because the second to last one is going to be n, because it's symmetrical, okay, which is another thing we learned from Pascal's triangle. So so if you've got a plus b to the power n, it follows this pattern, and we're going to talk about how to work these things out, okay, with an actual example. We need an actual example. We're going to let a be 2x and b be minus 5, and we're going to let n be 9, and we're going to do this expansion. We've already said the first one is always 1. Okay, this thing over here is 1, which is generating numbers from Pascal's triangle. Okay, a to the power n is going to be 2x to the power 9, yeah, a to the power n, there you go, 2x to the power 9, and then, following this pattern, which is the same as this pattern obviously, okay, you get 2x to the power 9, 2x to the power 8, 2x to the power 7, okay, and the minus 5, which is equivalent to your b, it starts with no b's, then 1b, then b squared, then b cubed, yeah, where b is minus 5, as I said, okay, and obviously we're adding each of these elements. The second one, this thing that's supposed to give you the second coefficient, that's always n, which is 9 in this case, so that's that. Okay, but let's actually work out one now, because we have to, right? This is not following any set pattern, this n2 bit. So what does n2 mean? Well, it means 9 2, because n is 9 and 2 is 2, obviously. Okay, and finally, what does that mean? Well, it means 9C2, 9 combinations 2, right? Okay, which is the button on your calculator, which is very easy to use. I've taken a screenshot of a picture of the very popular Casio calculators, which I definitely recommend, okay, and on the Casio calculators you've got the NCR above the division sign, so basically that means you have to press shift and then get to this button. So you press 9, shift, this button here, 2, and you get the answer 36. But you do need to know how to work it out, because sometimes they throw in a bit of algebra which requires you to work this stuff out, okay? So how do you work it out? I'm just going to show you with numbers, obviously, just to teach you the principle of how to do it, or the technique at least. And so how does it work? Well, the 9 on the top of this bracket goes to the top of this, and you do 9 factorial. That's a question mark, by the way. Yeah, actually, let's talk about that. Factorials, useful info. N factorial means n times n minus 1 times n minus 2, all the way to 1, which in practice means this. 4 factorial means 4 times 3 times 2 times 1. Okay, and 0 factorial, which doesn't really follow the normal rules, is just equal to 1. Okay, you don't get minus numbers or fraction numbers, it always has to be whole numbers. Okay, so that's factorial explained. So let's carry on with it. So 9 factorial obviously means 9 times 8 times 7 times 6, blah blah blah, all the way to times 1. Okay, you can see the crossed out for a reason, you'll see in a second. So the top bit does that, 9 factorial, and the bottom bit goes here, 2 factorial, and then you combine those two by taking them away. 9 take away 2 produces the other factorial bit. So basically it becomes 9 factorial over 2 factorial times 7 factorial. Okay, which I've written here. You've got 9 factorial, there you've got 2 factorial, which is just 2, and so 7 factorial, which is 7 times 6 times, blah 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 blah, all the way to 1. Now you can see they're crossed out because they're cancelling out. Okay, this 7 counts with a 7, 6 with a 6, and that's quite normal, which basically reduces massively your working out. Okay, so, and it always works like that. If I started with a 6 factorial on the bottom, it would have cancelled everything above it from starting from 6 onwards. Yeah. So anyway, you're left with 9 times 8 divided by 2, which is basically, you know, the 8 cancels the 2 as well, isn't it? So basically it's 9 times 4, which is 36. So that's how you do that. Now, there is another method, another shortcut, I should say, for a very specific situation, and I don't teach that because my general method is to teach you as little as possible so you can just understand it and get on with it, because I remember it was very hard when I did it to memorize everything, so I tried to get you to memorize as little as possible. Now, some kids, some students are going to could have already done C4 and they're just taking C2 again or something, right? And they would have learnt this other expansion. So if you want to know this other shortcut, go to binomial expansions for C4 and you'll see it there, okay? If you really want to. Now, finally, estimating using binomial expansions. Well, for example, this, you got use 1 plus x over 2 to the power 7 to estimate this stuff. What's the relationship? Well, they look pretty similar, don't they? So basically, we're saying this is the same as this. So when you expand this, where it expands like this, okay, if I put the right value of x, we've got the same situation, right? Okay, so I've got 1 plus x to the power 7 to estimate this. So that means I'm basically saying 1 plus x over 2, sorry, to the power 7. So 1 plus x over 2 is the same as the 1.005. Okay, I don't need the bracket there, by the way. I just wrote it so it looks similar and easier to compare. So that's equal to that, and if you rearrange that, you can easily work out that x has to be 0.01. Okay, now once you sub that value into the expansion for 1 plus x over 2 to the power 7, which this means roughly equal to, this expands to this, up to that squared. You know, this expansion can keep going on and on and on. Okay, but what we tend to do is just expand it for the first 3 or 4 terms of the expansion or elements of the expansion, okay? Because what they're saying is if x is really small, then x cubed and x to the power 4 might be so small that we can ignore it. Depends on what you're doing really in real life, but they all just basically tell you how far to go and what's important, what's not, how far in the expansion it's worth going. Okay, so you do that. Say in this expansion they want you to go up to x squared, so you'd go up to there, and then you put in the value of x so that it's equivalent to this. Okay, and so these two things are made equivalent basically. So in this case x is equal to 0.01. Stick that into this expansion. Can you see I replace the x with 0.01 and you work that out and it gives you 1.0895, which is roughly equal to what is it, 1.005 to the power 7. And that is the end of the video.